Welcome back to the Network Plus training series. In this lesson, we are covering Objective 2.1, Explain Characteristics of Routing Technologies and Bandwidth Management Concepts. Routing is what connects networks together. Without routing, the internet as we know it would not exist. In this lesson, we will cover how routers make forwarding decisions, the differences between static and dynamic routing, the most common routing protocols you will see on the exam, and the bandwidth management techniques that keep traffic flowing predictably. Let's get started. A router operates at layer 3 of the OSI model. While a switch uses MAC addresses to forward frames within a local network, a router uses IP addresses to forward packets between different networks. Every time a packet arrives at a router, the router examines the destination IP address, consults its routing table, and forwards the packet out the correct interface toward its destination. This process repeats at every router along the path until the packet reaches the destination network. The routing table is the core of how a router makes decisions. Each entry in the table represents a known destination network and contains several key pieces of information. It includes the destination network address and its subnet mask or prefix length, the next hop IP address or the outgoing interface, the administrative distance, and the routing metric. When a packet arrives, the router looks for the best match in this table. If multiple routes match the destination, the router uses a rule called longest prefix match. This means the route with the most specific subnet mask wins. A route to 192.168.1.0/24 will be preferred over a route to 192.168.0.0/16 because the /24 is more specific. Routes can enter the routing table in two main ways: static routing and dynamic routing. Static routing is when an administrator manually configures routes on the router. The administrator specifies the destination network and the next hop. Static routes are simple, predictable, and consume very little CPU or memory. They work well in small networks or for very specific paths. However, static routes do not adapt to network changes. If a link goes down, the static route remains in the table and can cause traffic to be dropped unless an administrator intervenes. A special type of static route is the default route, also known as the gateway of last resort. It is written as 0.0.0.0/0 and matches any destination that is not in the routing table. Default routes are extremely common on edge routers and end-user networks, pointing toward an internet service provider. A floating static route is a backup static route configured with a higher administrative distance than the primary route. It sits inactive in the configuration and only becomes active if the preferred route fails. Dynamic routing, by contrast, uses protocols to automatically discover and share routes between routers. When a new network is added or a link fails, dynamic routing protocols update all affected routers within seconds. This adaptability makes dynamic routing the preferred choice in medium and large networks. When multiple routing sources provide a route to the same destination, the router needs a way to decide which one to trust. This is where administrative distance comes in. Administrative distance is a numeric value that rates the trustworthiness of a routing source. Lower is better. A directly connected network has an administrative distance of 0. A static route is 1. Internal EIGRP is 90, OSPF is 110, RIP is 120, external BGP is 20 while internal BGP is 200. When two protocols advertise the same route, the router installs the one with the lowest administrative distance. Once the protocol is chosen, the metric is used to pick the best path within that protocol. The metric varies by protocol. RIP uses hop count, which is simply the number of routers a packet crosses. OSPF uses cost, which is based on link bandwidth. EIGRP uses a composite metric that factors in bandwidth, delay, and other values. BGP uses path attributes such as AS path length. Let's look at the major routing protocols. RIP, or Routing Information Protocol, is the oldest dynamic routing protocol you will see on the exam. It is a distance vector protocol that broadcasts its full routing table every 30 seconds. It uses hop count as its only metric and has a maximum hop count of 15. Any network 16 hops away or more is considered unreachable. RIP is simple to configure but does not scale well and is rarely used in modern networks. OSPF, or Open Shortest Path First, is an open standard link state protocol. Instead of sharing its routing table, each OSPF router builds a map of the entire network topology and runs the Dijkstra algorithm to calculate the shortest path to every destination. OSPF supports areas, which allow large networks to be broken into logical groups. Area 0 is the backbone area, and all other areas must connect to it. OSPF converges quickly, uses multicast for updates, and is the most common interior routing protocol on the exam. EIGRP, or Enhanced Interior Gateway Routing Protocol, was originally a Cisco proprietary protocol and is now open standard. It is a hybrid protocol that combines features of both distance vector and link state routing. EIGRP uses an algorithm called DUAL, the diffusing update algorithm, to calculate loop-free paths. It converges very quickly and uses a more sophisticated metric than RIP. EIGRP is common in Cisco-centric networks. BGP, or Border Gateway Protocol, is the protocol that runs the Internet. BGP is a path vector protocol used to exchange routing information between different autonomous systems. An autonomous system is a collection of networks under a single administrative control, such as an Internet service provider or a large enterprise. Every AS is assigned a unique number, and BGP uses these numbers, along with path attributes, to select routes. BGP is complex, slow to converge compared to OSPF or EIGRP, but it is designed to handle the massive scale of the global Internet. This brings us to the difference between interior and exterior gateway protocols. Interior gateway protocols, or IGPs, run within a single autonomous system. RIP, OSPF, and EIGRP are all IGPs. Exterior gateway protocols, or EGPs, run between autonomous systems. BGP is the only EGP in widespread use today. Before a router can forward a packet on a local network, it needs to know the MAC address of the next hop. This is where ARP, the Address Resolution Protocol, comes in. ARP resolves an IP address to a MAC address by broadcasting an ARP request and receiving an ARP reply. The result is cached in the ARP table, so the router does not have to ask again for every packet. On the local network, hosts also need redundancy for their default gateway. If the default gateway goes down, hosts cannot reach any network beyond the local subnet. This is solved by first-hop redundancy protocols, or FHRP. The three you need to know are HSRP, VRRP, and GLBP. HSRP, or Hot Standby Router Protocol, is a Cisco proprietary protocol where two or more routers share a virtual IP address and virtual MAC address. One router is active, and the others are standby, ready to take over if the active router fails. VRRP, or Virtual Router Redundancy Protocol, is the open standard equivalent of HSRP and works in a very similar way. GLBP, or Gateway Load Balancing Protocol, is also Cisco proprietary, but it goes a step further by actively load balancing traffic across multiple routers simultaneously instead of keeping standby routers idle. Now let's shift to bandwidth management. Networks carry many different types of traffic, and not all traffic is equal. A voice call or a video conference cannot tolerate delay, jitter, or packet loss, while a file download is much more forgiving. Quality of service, or QoS, is the collection of techniques used to give important traffic the treatment it needs. QoS starts with traffic classification and marking. At layer 2, inside an 802.1 QVLAN tag, 3 bits are set aside for class of service, or COS, giving us values from 0 to 7. At layer 3, inside the IP header, we use Differentiated Services Code Point, or DSCP, which provides 6 bits of marking in the TOS field. The DSCP is the modern standard and is what you will see in most enterprise networks. Common DSCP values include expedited forwarding for voice traffic and assured forwarding for business-critical applications. Once traffic is classified and marked, the network applies policies to enforce the desired behavior. Traffic shaping delays packets that exceed a defined rate, buffering them, so the overall rate stays within the limit. This smooths out bursty traffic. Traffic policing, by contrast, drops or remarks packets that exceed the rate without buffering. Shaping is usually applied outbound on a router, while policing is typically applied inbound. When interfaces get congested, queues decide which packets get transmitted first. First in, first out, or FIFO, is the simplest queue. Whatever arrives first is sent first. Weighted fair queuing, or WFQ, gives each conversation a fair share. Low latency queuing, or LLQ, reserves a priority queue for time-sensitive traffic like voice, guaranteeing it will be transmitted before anything else. LLQ is the standard choice for voice and video networks. The broader framework most enterprises use is called Differentiated Services, or DiffServ. DiffServ treats traffic by class at each hop, rather than reserving end-to-end paths. It scales well, which is why it has largely replaced the older integrated services, or IntServ, model that used protocols like RSVP to reserve bandwidth end-to-end. Let's wrap up with a quick review. Routers use layer 3 IP addresses to forward packets between networks, using the routing table and longest prefix match to pick the best path. Administrative distance ranks routing sources, and metrics rank paths within a single protocol. Static routing is manual and predictable. Dynamic routing adapts automatically. RIP, OSPF, and EIGRP are interior gateway protocols. BGP is the exterior gateway protocol that runs the internet. ARP maps IP addresses to MAC addresses on the local network, and FHRP protocols like HSRP, VRRP, and GLBP provide default gateway redundancy. Finally, QoS classifies, marks, shapes, polices, and queues traffic so that voice, video, and business-critical applications get the performance they need. Thank you for watching this lesson on Objective 2.1. In the next video, we will cover Objective 2.2 on switching technologies and features.